planet.
Hi everyone, and welcome to yet another
The Earth is Flat on Planet Pluto,
an online cosmic talk show about astronomy, science, and other stuff where the guests are the clear highlight and where you can ask any questions and also participate by using the chat on this side. Now, every Wednesday at 5:30 p.m. UK time, we have been bringing you a cosmic topic and amazing guests who share their passion for science and space. This is apparently already the 6th episode in English, but just like in all others, things can and will definitely go wrong. I must stress that this is obviously part of the scientific method. I mean, like blowing things up. And don't be surprised if the sound stops or if the image stops, or if, for example, one of our guests doesn't show up, because when things work perfectly, we never really learn anything at all. During June and July, I'll be your host as we attempt to bring you lots of astronomy, science experiences, the human side of looking up, and also a lot of fully random, but hopefully fun stuff. My name is David Sobral. I'm an astronomer and a scientist. Just like everyone else on this amazing yet insignificant planet, I'm 10% made of cosmos and 90% made of stars, which formed billions of years ago. In our galaxy, apparently stars are still forming, but at a relatively low rate, something like a few stars like our sun per year in the entire galaxy. But some galaxies are way more hyperactive. Some are forming or form the equivalent of something like hundreds, thousands of suns per year in these huge bursts of star formation. These superactive galaxies are very rare in the present universe, but they become much more common in the past. How can galaxies be that active? Why are those galaxies so damn dusty? Did people just forget to vacuum clean them? It turns out that apart from forming stars and all that goes along with them, like space rocks, planets, dust, and the elements that keep us alive and make most of us, centers of galaxies also host these mysterious supermassive black holes. How did they get there? How did they form? Do they know about the galaxy they live and grow in? Are they that massive because smaller black holes kept merging like these two that just did it somewhere in the universe? Do they ever blow up and detonate entire galaxies? Does this ever happen in the real universe? Do galaxies grow with their black holes in a sort of symbiotic alliance? Or are supermassive black holes more like galaxy parasites? Should we be worried about supermassive black holes, for example, in the center of our own galaxy? Today's guests are experts in supermassive black holes, their activity, their host galaxies, but also on superactive dusty galaxies and on the growth of galaxies and their central supermassive black holes across cosmic time. They will tell us all about these fascinating fields and also, by using Galaxy Zoo, how you can contribute yourself. Remember that you can directly participate and ask questions by using the chat on this side on YouTube, and the voice from beyond will read your questions to our amazing guests. For now, though, let's welcome today's guests, Brooke Simmons, Julie Wardlow, and João Calhau, who hasn't been able to join us, but we're still going to welcome him. So thank you so much for coming into the show. I hope you're all doing very well. And Brooke, I would start with you and just to introduce you for those that don't know you, and hopefully I get everything correctly. So you got your PhD from Yale University on the other side of the pond, after which you moved to Oxford to take on a research fellowship. So I assume that maybe the weather wasn't perfect, so you decided to move back to the US to UC San Diego, where you were an Einstein Fellow. That's incredibly competitive for those of you that don't know it. For a few years before you joined Lancaster University in 2018 as a lecturer in astrophysics. Among many other things, you are the deputy project scientist for the spectacularly popular Galaxy Zoo project and the principal investigator of several projects. So your research focuses on galaxy evolution and coevolution of galaxies and their supermassive black holes. So this sounds really, really impressive. But first of all, for people that don't know, what the hell is a black hole?
Yeah, it's a good question. First, thanks for having me. This is great and really fun. And hello, YouTubers. Please do ask any questions you like. So black holes are simultaneously kind of exotic objects, but also quite simple at heart. They're just really, really dense, just stuff that's really, really dense, much more dense than you would see on Earth, thankfully. If you were to take the sun, everything that is the material in the sun, and collapse it to something the size of Lancaster, where I live, or like a small city, that would become a black hole. But you have to get it to that point. So that's actually quite difficult to do. But it's basically just gravity. And a black hole is what happens when gravity wins over everything else. Gravity is always trying to make everything into a black hole. And the only reason that the whole universe isn't a black hole is because it's actually not that strong a force compared to all the other forces that like hold atoms apart and so on, keep you and me in the shape that we're in, that sort of thing. So a black hole is a nice exotic thing that we don't come into contact with very often, except in distant telescopes, but they're pretty cool.
So I guess even though the other forces are quite complicated to study, we should thank them for not being all just black holes in the universe. And
indeed, otherwise physics would be pretty boring.
When we talk about supermassive black holes, how supermassive are we really talking about?
Yeah, so that's actually like an official category because astronomers, we're weird about naming things. Sometimes we give things names that are like these weird sets of letters and numbers that are based on coordinates and have no meaning. And then other times we're like, let's just call it supermassive. But what we actually mean is that that is something that is around maybe 100,000, a million times the mass of the sun, of a single black hole is that mass, up to the biggest one that we have seen is around 10 billion times. So that's many orders of magnitude difference between those. And those live in the centers of galaxies. Now, there are less massive black holes. You can have black holes that are similar in mass to a single star. And those happen as like the endpoints of the evolution of very massive stars. And then we have, we are sort of discovering black holes that are growing up in size and can be tens of times, hundreds of times. And we've seen what we call intermediate mass black holes, which are smaller but are still big, like thousands of times the mass of a single star. But supermassive has like a specific meaning, and it generally means like at least 1 million times the mass of a star.
At least it's definitely well defined, and like many other things in astronomy. And so when we talk about these black holes being massive and separating according to their mass, if they're black, how do we even know how massive they are?
Yeah, there's a couple ways. This sort of the obvious way, I guess, is that you see the effects they have on everything around them. So that's how we have studied the black hole that's in the center of our galaxy, which is Sagittarius A star, or Sag A star for short. That black hole is pretty kind of quiet. Nothing much is happening around it, although there are lots of stars orbiting around it. And so you can look at the orbits and you can calculate, again, based straightforwardly on gravity, what they have to be orbiting around. Like, what is the mass that they're orbiting around? And that's a quite high mass. It's millions of times the mass of a star. And there's nothing there. And that has to be in such a small space because of the size of the orbits that it's so dense that it has to be a black hole. So you can kind of make that logical argument that's based on gravity. And that's one way that we've observed that. You can also do more complicated modeling where you look at larger groups of stars or gas in a larger area, and you do a modeling of the orbits, and you find that there has to be a really incredibly dense thing at the center, and it has to be a certain mass such that it has to be a black hole. And then the thing that I study a lot is actually when there's stuff falling into a black hole, before the matter falls in, it gets very hot, it heats up, it becomes energetic, and it radiates. And so it's not really contradictory, but it's not intuitive that in fact, these supermassive black holes, when they are actively growing, are some of the most luminous objects in the universe. And so then we can see that radiation directly.
And I guess an important question is, we're seeing an artistic impression, just for people that don't know, we can't get these details yet. But can we explain why these things exist in the centers of pretty much every galaxy? Do we understand that?
Yeah, I mean, it's kind of a source of ongoing research, the exact procedure for how that happens. But I think I would say that more or less what we think is that it's not that hard to form a black hole. Everything's trying to become a black hole, and there are certain ways to make black holes by exploding stars. And maybe in the very early universe, you can do that just by directly collapsing a cloud of gas without going through any star formation phase at all. And if that happens, and if then black holes only grow. Black holes of the size that we're talking about, stellar mass type black holes or bigger, they don't really shrink appreciably over the age of the universe. So they're only going to get bigger. And when you have that object then that is in a complex system that's orbiting with lots of other things that are all generally smaller, when they interact in gravity with like an orbit, what tends to happen is that the smaller thing, like the star that's passing by the black hole, tends to gain energy. And then the black hole, the larger thing, tends to kind of sink to the center because it loses energy. And so you end up pretty quickly with a black hole at the center. And then that black hole just keeps growing, and how it starts out and how it becomes supermassive, it has to grow somehow. And so you drive material towards the center, and that's how it grows. And that's why they're in the center. And that's why probably every galaxy has one, or almost every galaxy.
And do we have an idea of whether they kind of just grow equally in all kinds of galaxies? Or are there specific galaxies that are better at feeding and nurturing their supermassive black holes?
Yeah, it varies a lot. I mean, it varies a lot, but it all tends to kind of average out to the same answer, which is that we look at galaxies that are kind of small, dwarf-ish galaxies, and we look at galaxies that are huge, the biggest galaxies that we can observe in our universe. And we see a pretty fixed ratio between the mass of the black hole, which is less than 1% of the total mass in stars in the galaxy, and then that mass in stars. It's about like, yeah, it's about 1,000th or so. So that tells us that like over time, on average, the way that the black hole and the galaxy have to grow together has to lead to the same place where they have that same mass ratio. But how that happens can change a lot based on the circumstances. It can be a kind of like flickering, like slow and steady. Sometimes a little bit comes on like a trickling. Or we think that's more or less probably happen most of the time in the Milky Way, or it can be a really major event, like you can have a train wreck collision of two galaxies where everything gets mixed up, a bunch of stuff falls to the center, and then it grows really fast by eating a lot of stuff really quickly. Those are very luminous, but that doesn't tend to last very long. So you can get a really different kind of profile of like the life cycle of these black holes.
And we'll definitely come back to that and to specifically how they may grow in, for example, different environments, whether galaxies need to merge or not. Before we do that, I'd like to introduce Julie Warlow. So Julie, you got your PhD from Durham University before you moved to the USA, I think, as a research fellow to work at UC Irvine, way better climate than here in the UK. You then returned to Europe. You were a fellow at the DARK Center in Denmark, Copenhagen. I always love the name. And you then came back to the UK and Durham, where you were awarded a super competitive STFC Ernest Rutherford Fellowship. And in 2018, you joined Lancaster as a lecturer in astrophysics. Now, your research focuses on galaxy formation and evolution, and particularly I would say you really love dusty star formation, dusty star-forming galaxies, and these superactive galaxies. They are forming stars as if there is no tomorrow. Now, when we talk about these superactive galaxies, just how active are we talking about?
Hi, yeah, that's a great question. Thank you for having me, and it's great to see so many people watching. So active galaxies, these really high star formation rate ones, they're forming stars about 1,000 times quicker than the Milky Way. So we measured the star formation rate in terms of how many solar masses, so how much mass like the same as the sun forms in a given year. And of course we have to time average things because things in astronomy are quite slow, but the Milky Way is forming stars at a few solar masses per year, 1 to 2 to maybe 3. And these galaxies that we're talking about are 500 to 1,000 times quicker than that. So the amount of new stars formed it's just constant all the time, these massive bursts of star formation.
And I mean, why are these active galaxies so dusty when they're forming so many stars?
Yeah, so it's not so much the formation of stars that causes the dust as the death of other stars that causes the dust. So when you have this big burst of star formation, you create lots and lots of young stars, and some of those are really massive. And the most massive stars die very quickly, and they run out of their materials very quickly. And when they do that, they explode. And when they're in that process of explosion, the supernova, they create a bunch of dust. And that's then spread throughout the whole region that is still forming new stars.
And exactly how can you find and study these galaxies? So we're seeing some images, for example, in the more infrared and longer wavelengths. How exactly do you do this?
Yeah, so in order to really find these galaxies, we have to look for the emission from the dust, because the emission from the stars is all hidden in the dust. It's a bit like if you had a lot of smoke coming out of something, you might not necessarily be able to see the fire behind it because the smoke blocks your view. And in this case, the dust is blocking the view to the newly forming stars. And so what we do is look from the heat that dust is producing. So the dust is warmed up by the stars that are forming, and we can measure that heat. And so we look at long wavelengths. So we look at infrared, which means that your eyes would never be able to see it no matter how big they were, but we can have telescopes and instruments that are sensitive at those long wavelengths.
And do these like super active galaxies that are forming almost thousands of suns per year, do we know if they also contain a pretty big supermassive black hole?
Yeah, we think they do contain supermassive black holes, purely because every galaxy is thought to contain a supermassive black hole, as Brooke mentioned, and there's this tight correlation locally between the mass of the galaxy and the mass of the black hole. With these particular galaxies, it's really tricky to understand what's going on with the black hole, because most of the time, the dust and the emission from the star formation washes out any signal from the black hole. There's a small fraction of them, maybe 10 to 20%, that we can see evidence that there's a black hole that's growing, and there's a black hole that's growing very, very rapidly. But if they have black holes that aren't growing very rapidly, we wouldn't be able to detect that with our current instruments.
And I guess an important thing to also cover is just about how common are these galaxies, for example, around our own Milky Way in the present day universe. Are they easy to find, or are they quite rare?
Yeah, these galaxies are pretty rare. They're extremely rare in the local universe. So near to the Milky Way, we don't find very many of them at all. And so for many years, it wasn't really considered that this sort of galaxy growth was very important, because locally there's not much of it. But once we got new telescopes in the late 90s that were sensitive, that you could look at further and further away galaxies, we found that there was actually a lot more than was expected based on the local statistics. So overall, there's not very many locally, but when we go to about 10 or 12 billion years ago, there's a lot more of them. They're still incredibly rare though. So there's more compared to local, but they're still rare. And it's probably something to do with the timescales that goes to that rarity, because they're not active for very long.
And you kind of mentioned those timescales already, but in your research, whenever you're trying to find and study these super active galaxies, typically how far back in time are you seeing?
Yes, so we're looking mostly 10 to 12 billion years ago is where the majority of them are. There's some a little closer to us than that, and there's some much further away. We found some up to about 13 billion years ago, which is very close to the Big Bang, but we don't know how much closer they go. It seems like every time we find a new one that's a bit more distant, everyone's surprised, because really there shouldn't be that many that close to the Big Bang, and yet we still keep finding them.
And Brooke, so in terms of these supermassive black holes, and also in the context of these monster galaxies that form a lot of stars, in this context, should we be seeing the black hole as some sort of parasite inside a galaxy? I mean, is it a bad thing for a galaxy to have one of these supermassive black holes, or are they in kind of a symbiotic relationship for most of the time?
We think that it probably is more of the latter, but it can vary. So for example, you can think of a black hole as like feeding off of its surroundings because that's how it grows. I mean, material falls towards the center, and so and that falls into the black hole eventually. But all of the luminosity, all of the energy that gets radiated from around the black hole region, when that happens, can actually drive new stars to form in the galaxy. So we've seen that kind of feedback and interplay happen. If it gets energetic enough, it can actually shut down the star formation though. So it's really kind of both of those things can happen. They can both happen at different times in the same galaxy, or they can just happen differently in different galaxies. So it's really just kind of a bit of a hot mess, I would say. But definitely they do, we observed over like a large population of galaxies. Obviously we can't observe one galaxy for many billions of years, except in a computer simulation. But in the observable universe, we observe the whole population in this kind of sort of standard relationship. And so we assume that there is a kind of on average symbiosis between the level of star formation and the level of growth in the black hole.
So an important thing to also consider, especially for those that never consider that people are talking about these things, supermassive black holes growing, I don't know, billions of light years away, and this symbiosis between galaxies and supermassive black holes. In practice, how on earth do we know how quickly a supermassive black hole is growing? I mean, it is black, it's incredibly distant. How do we know how fast it is growing?
Yeah, actually, the first one that was ever observed, there was a huge argument. It was in the 60s. There was a huge argument over whether that's what it was or whether it was something else, like a new kind of star or something. Because if it was a black hole or some distant energy source, because we thought it was some distant source of radiation, it had to be so incredibly bright that we couldn't figure out what it was. And it actually was a long time until we worked out that it had to be black holes as sort of the engines powering it. But the way that we observe them is, well, so black holes are, the structures around a growing black hole are quite complex and they're not symmetric. So like these diagrams show you this is like a disk. So as the material comes and falls in, you get a kind of disk of stuff that's kind of spiraling in towards, and you can get these jets that shoot out, and there's this kind of hot corona. In some cases, you can have these more extended, like very dusty, like shells, which we will call a torus sometimes, but they don't always look like a kind of donut. Sometimes they're more kind of clumpy and cloudy, but a little bit more coherent. And so they're not symmetric. And what that means is that if you're looking at this system, what you observe really depends on the angle you're looking at it from. And that's kind of random on the sky for any given galaxy. And so you can observe, if you're looking through the dust, I mean, Julie already mentioned that the dust gets heated, and so it radiates in the infrared. It like reprocesses that radiation, and it radiates in the infrared. So you can detect the signatures of black holes because they get heated to a higher degree, to literally a higher temperature than star formation alone can do. And so we can look at different wavelengths and we can look for different energetics. If you're looking like straight on, you can see the jet, you can see relativistic effects. If it's somewhere in between, you can see X-ray signatures and optical signatures that are very unique and really can only be created by something with the energetics that you only see around black holes. So even though they are very distant, because many of them are very, very luminous, they're actually not as hard to detect as you might think.
And Julie, so the other aspect, so I guess Brooke told us a little bit about how we can measure the growth of a black hole and that it might be complicated depending on the viewing angle. What about measuring the growth of a galaxy? So measuring that how many stars a galaxy is forming, how do you do that?
Yeah, that's a great question. So there's a couple of different ways you can do it, and a lot of it depends on what type of galaxy you're trying to measure. So for these really, really active ones, we use the infrared to measure that growth rate because we can observe a correlation between how many stars are forming, so the growth rate of the galaxy, and how much light is emitted in the infrared. And so by looking at how much light we're detecting in those long wavelengths, we can calculate how many stars are forming. You can also do similar things at shorter wavelengths, so optical. So if you had giant space eyes, you would be able to see at those wavelengths. But those are affected by dust. So if you've got a galaxy that you know has loads of dust in it, then any calculations that you make in that region, you have to correct for the fact that the dust is blocking some of the light.
And I guess the other important question is, so if supermassive black holes and their galaxies they grow hand in hand, right, as far as we can see. So is this a question of like the chicken and the egg? So what exactly comes first? Brooke, do you want to have a go at it?
The TLDR is I don't know, and nobody does. I think it's probably both, is my guess, and it probably depends a little bit on the conditions around any given newly forming galaxy will have various properties: size, mass, temperature, density, all of this stuff. And so in those situations, whether it like forms stars first, at which point we would probably then call it a galaxy, and then it makes black holes, and then that is how that works. Or whether you first have like this cloud of gas just gets the right conditions to collapse straight into a black hole, around which there's then enough gravity for other things and stars start forming around that, at which point we then call it a galaxy. It's probably a bit of both. Probably depends.
Julie, would you agree? You don't want to commit to just one?
No, definitely. I think that's completely right. There's so much interaction between the two parts, and the same things are likely to be fueling the supermassive black hole, and as is fueling the growth of stars. So to make stars, we need incoming gas, and we need that gas to be cool. To grow the black hole, you need incoming material, and a lot of that can be gas. It doesn't matter so much about the temperature for the black hole. So there's a little bit of a trade-off there, but whatever is causing gas to infall is probably causing material to infall into the black hole as well.
So I guess it's very hard to grow, I guess, one without growing the other. And exactly. Before we move on, I guess we have at least a couple of questions from YouTube for both of you, I assume.
Yes. So Weather asks, what's your favorite galaxy object in the universe? And where can I get my giant space ice?
Giant space eyes come with telescope proposals, I think.
It's a little bit of a hack that you have to, a mechanical hack. Favorite object. I'm torn. That's really hard to decide. I think on the one hand, I want to say like Sagittarius star, the supermassive black hole that's at the center of our galaxy, is so cool. I love the fact that like it exists, we can study it. There are a couple of groups that have kind of made careers out of really getting to the details of that. And you actually have to look through the dust that's in our galaxy to see to that. And it's really difficult work that they do. It's really cool. And just looking at the animation of the movie of the stars orbiting and how they know where it is just like, it's mind boggling, even though I don't study that particular black hole at all. I really like it. I'm looking forward to hopefully the Event Horizon Telescope observing that at some point. I think they did M87 first because they didn't have as much like noise and dust and stuff that they had to look through, and it's much less messy over in that galaxy than it is in our own galaxy. So hopefully we'll see an image that'll be sort of like this, but around a very different kind of black hole, and we can compare them and start to understand how things vary in different systems. I'm really looking forward to that. I think that'll be really cool. But then also a long time ago, the Galaxy Zoo volunteers decided on their own to create an alphabet out of galaxies. So this exists. There's a galaxy alphabet. I think we're actually moving our servers right now, so that website is currently down. It used to be like writing.galaxyzoo.org. But there's like a galaxy that's shaped like a question mark. There's a galaxy that's shaped like a semicolon. There's a galaxy that's shaped like a square. I don't know how that happened, but that's a cool orientation, gravitational effect. And I kind of, that as a whole population of things, I kind of adore that too. So.
And Julie, do you have a favorite galaxy or object?
Yeah, again, it's a really hard question to answer that. In terms of beautiful pictures, I love a good spiral galaxy that's nearby. But my favorite image is one that's taken from ALMA, and it's an image of a gravitationally lensed galaxy. So it's shown here. So the red galaxy here is something that's in the background, and that's forming loads and loads of new stars. And the blue blob that you see in the middle is a galaxy that's in the foreground. And the mass of that blue galaxy is lensing this background galaxy to make it look like a circle or almost circle. And so by using this gravitational lensing effect, and that works, just like Brooks glasses or similar things, we get a magnification of that background galaxy. So it's distorted, but the magnification allows us to see incredible detail in that galaxy. And so we can really study it in ways that we wouldn't be able to otherwise. And this image just really summarizes how that technique works, and you can see all the features in it that we normally wouldn't be able to.
And I think before we move on, we also have a question, might be for Brooke, from Pedro.
Yes, so Pedro asks, what instruments are you used to study the black holes?
I think the easier question might be what instruments aren't used, possibly. So like if we stay on ALMA, for example, I haven't used ALMA myself to study black holes, but I know people who do. And I know I know a collaborator, for example, who uses ALMA, which has amazing resolution, and studies the gas that's around quiet black holes, where you don't see the luminosity from that system directly, but you see the galaxy around it. And they do this kind of gravitational modeling. And because ALMA is so high resolution, they can do it even in quite dusty kind of gaseous galaxies. And that's amazing to me. A lot of the stuff that I work on, we first kind of detect the black holes using X-rays. Because that tells us a lot of information about kind of the structures around the black holes and about what our orientation is and stuff. And so we'll look at it using the Chandra telescope, which they're in space. You can't see the X-rays from the ground, or XMM. And there's a new mission called eROSITA that's just starting to come out with data, but it's going to be a long time for us to wait for the public releases for that. But that's going to be really cool. And then, you can look at black holes at basically any wavelength. I mean, they radiate across the entire electromagnetic spectrum. So you can look at radio telescopes all the way up to X-rays and throughout. And they're basically not resolved in any of them unless you have something like the Event Horizon Telescope. That's the only one that can resolve them. So we're always studying a single point of light. And
Brooke, I guess one of the things that, so Julie told us that she looks back in time quite a lot to find these super active galaxies. I assume you still go back in time a little bit, but maybe not as much. Could you give us an idea of what kind of galaxies you're studying, how far away they are, and how much you're looking back in the past?
Yeah, so in the past, I have in previous research projects and so on, I've looked back to as far as about 11 billion years ago, approximately. So that's about Redshift 2 for those who use Redshift. And that's pretty far back. It's certainly at a totally different part of the universe where there was a lot more active star formation and so on, and a lot more active black hole growth. Right now, I have tended to be looking at things that are a little more nearby. And part of that is because one of the things I'm really interested in is studying the kind of black hole growth that is like the low and slow, like fairly calm, and not the rock stars that are like the train wreck mergers and stuff, but the stuff that's sort of just happening just kind of quietly and unassuming. And that requires that there be no interactions happening. And it particularly puts some constraints on how the structures of the galaxy has evolved, because that's how we can tell that a galaxy hasn't had a merger. And in order to see those, I need really well-resolved images. And so it kind of constrains me to be nearby. And that then has the advantage of looking at a galaxy that has had the whole age of the universe to evolve. So it's really varied a lot. But right now, I guess most of my work is looking back, millions of years as opposed to many billions of years.
And connected to that, so we were talking about when lots of gas come into a galaxy, both the galaxy and the supermassive black hole grow. But one of the things you try to look at is ways in which the supermassive black hole can grow without a lot of gas coming in, right? So is that possible? And how?
Oh, for it to grow without a lot of material?
Yeah.
I mean, definitely. I think even Sag A star it's got a little bit of stuff trickling in. And we've actually seen incidents with this galaxy, and we've now seen them in other black holes and other galaxies as well, where you have like a single star that gets too close, gets disrupted and falls in. And so you can see that, but it's a very low kind of signal type of an event. Those are single events. What might be more likely is that you just have a little trickle of something falling in. And so that then is much harder to detect, because when the thing is whopping and booming and very energetic, you can easily pick it out. It can be like dominant. You can sometimes just see it in the image. It's like it looks like a really bright star right in the middle of a galaxy. But if it's a lower luminosity thing, you can't see it. So it's harder, but based on all of our models and our statistical like inference and all the kind of very detailed work, we really think that that population of galaxies where the black hole is just kind of like plodding along in its growth, that is actually quite important, because that's more normal. And so that's actually how they spend most of their life. And so it's important to understand them in that phase too.
So, and also as part of your research, I mean, you were heavily involved, you still are, with Galaxy Zoo, and you also use it. So could you tell us a little bit more about what Galaxy Zoo is and how people can get involved?
Yeah, Galaxy Zoo is a project where we ask the public to answer some basic questions about the shapes that they see in galaxies. I mean, one of the great things about galaxies is that the shape that you see, like whether a galaxy has a spiral pattern in its stars and dust or not, tells you really quite a lot about the physical conditions that are occurring in the galaxy now and that have occurred in the past. And then there are other things too that can tell you about what might be likely to happen in the future. So you actually can learn a huge amount about the physics of galaxy evolution just by looking at the shape. And the shape is like readily available to any person, even if they have no previous astronomy experience whatsoever. And then we also have, these new telescopes, and actually not so new anymore, survey telescopes that are looking at, thousands of galaxies, hundreds of thousands, millions of galaxies in the future. We're expecting billions of galaxies. And those details of the shape, some of which are quite complex and not easily understood by computer, are so powerful, but like a single science team member or even a whole team can't do them on their own. So we ask, if you go on to galaxyzoo.org, then we will ask you a question about a galaxy. It might be a series of questions about the galaxy. And then we will ask like around 20 other people the same question about the same galaxy, and we'll combine your answers. So it means if you're a little uncertain and you're still learning, it's fine. It'll all average out, and all of those answers are valuable. Plus the variability of the answers, if everyone disagrees, it tells us something about like how much information there is to learn. And that principle is something that we use in Galaxy Zoo because it allows us to like quantitatively measure things like how spiral is it, or things like that that are more like a qualitative question. We can quantitatively measure that, put like a statistical constraint on that, tell you how uncertain that is, and then we can use it in a different kind of analysis that if one person did it, it would be much harder to do. And those principles we then use across the whole Zooniverse. So I think right now, if you go to Galaxy Zoo, you will be asked questions about a survey that is looking in both the north and south. And then there are also some simulated galaxies from the latest generation of extremely high resolution, full hydrodynamic, all the cool physics simulations. That one's called Eagle, and those galaxies are in there too. There's also projects, if you were to go to zooniverse.org, you'd see Galaxy Zoo, but you'd also see other astronomy projects. I think the Disk Detective Project, which is discovering protoplanetary disks in our galaxy, has just restarted, for example. So those kind of principles where the public can make really authentic contributions to research that couldn't be done any other way, but only takes a few minutes, that's what we do.
It's really cool. So people should really get involved and check it out. Now, Julie, coming back to the superactive galaxies, one of the cool things that probably people can wonder is, so they can form up to something like 1,000 solar masses per year. Is there technically a limit? I don't know, is there like a competition between galaxies to know which one is the most star-forming galaxy in the universe?
Yeah, that's a great question. And the answer is we don't really know yet. There's a couple of things that limit just how many new stars can form in a single galaxy. And a couple of those I've already mentioned. So we need new gas to come in, and stars are formed out of gas that is compressed into small areas, and then it starts to collapse under its own weight. So we need that gas to be there, and we need it to be compressed together. But we also need that gas to be quite cool, because if it's warm, then it won't compress in the way that we need it to. So that means that if you've got something that is preventing gas from falling in, you end up without being able to form too many new stars. And similarly, if you've got something that causes the gas to heat up, then you won't be able to form too many new stars. So if you have a lot of current star formation, then that means you've got a lot of supernovae going off, because the most massive stars will explode in fairly short order. And that can prevent new gas from falling in, and it can heat up the gas. And so that then has a sort of feedback effect that stops many more new stars forming. And similarly, the black hole can have that kind of effect as well. So the black hole in the center of a galaxy can create winds from this disk that's heating, and that can heat up the gas that would be otherwise forming stars, and it can also expel it from the galaxy as well. So, you know, we've measured some star formation rates as a few thousand solar masses per year, so a few thousand times the mass of the sun in a year. But there's a lot of uncertainties on those measurements, and we have to bring models in to convert our observations into a measurement of that physical quantity. So there's not really a highest number that everyone, this is the maximum, and it does depend on the conditions in the galaxy because of these feedback effects.
And so when these superactive galaxies form a lot of stars, and at some point, if they run out of new fuel and there's no more fuel around, what does happen to them? I mean, do we have an idea of how these galaxies look like in the present after being so active?
That's a question that there's an awful lot of people working on at the moment. We have some ideas of what they might turn into because we know some of their properties. So for example, we can measure that these galaxies are very, very big. We know that they're forming loads and loads of new stars. And that suggests that they're probably going to end up being incredibly big galaxies in the local universe because they're already big 10 billion years ago. So they're going to end up even bigger by today. So the general consensus at the moment is that they're probably going to turn into what's called local elliptical galaxies. So these aren't the beautiful spirals that we see of the Milky Way and things like that, but they tend to be galaxies that are fairly red in color, and they're just kind of egg-shaped or spheroidal. And they don't have an awful lot of star formation going on at the moment. But you know, there's a big question mark over that, and there's some measurements that we're trying to make that would start to fill in the details a bit, but it's definitely a long-term question is to answer how these galaxies evolve over a long time.
And the other aspect, and Brooke already mentioned that she uses quite a lot of telescopes to study these supermassive black holes. What about you, Julie? Do you have favorite telescopes, and what kind of telescopes do you use?
Yeah, absolutely. I think, you know, my initial answer is very similar to Brooke's. What telescopes don't we use? We use a wide variety. The main ones, though, I think we could put in three categories. So firstly is what we call single dish far infrared telescopes. So these are telescopes that have one massive 15 to 20 meter dish. We don't call it a mirror because at the long wavelengths, you don't actually need a shiny surface. So we use technology like radio telescopes for the dish surface. And they're really good for surveying wide patches of the sky. And with those, we can pick out these individual galaxies, and then we can go and study them in more detail using other telescopes. So then we come on to my favorite telescope, which is ALMA, which is this one shown here. And that's an array. So there's 66 individual telescopes there, and they're all connected together. They all collect light at the same time, and that light is combined into a signal that we can then measure one galaxy in huge amounts of detail. So we get very high resolution, and we get very deep data. So we can see to high sensitivity what's going on in a given galaxy, and that works at far infrared wavelengths. And so it was a telescope like ALMA, in fact, it was ALMA that detected this red ring in this galaxy, and all of those little bumps and wiggles that you can see in that one are real signal. So that's real detection of dust in that particular galaxy. And then the third category of telescopes that I'd say I use a lot is going to be everything else. So those are the two main far infrared technologies. And then we'll use optical and near infrared telescopes to study what's happening to the existing stars in these galaxies. We might use X-ray or radio to study what's happening to the black hole in these galaxies. And so we really try to cover the full electromagnetic spectrum to get a complete picture of what's going on in these systems.
And I think before we talk a little bit more about your path and I guess your likings, there's at least a couple of questions, and probably we'll take first the one from Louis about like looking forward to the future.
Yes, so Louis asks, regarding black holes, what investigations or possible discoveries are you looking forward to it in the near future? Will new technology help us understand black holes better?
Do you want me to take that one? Short answer to the second question is yes, absolutely. So the new technology is maybe always helpful, I guess. But so I already mentioned the Event Horizon Telescope, right? That involved developing new technology and bringing together different technologies and figuring out how to combine all of that. So it was a combination of like known physics and new technologies. So I'm looking forward to what that's going to tell us in the future, because it's really only just got started. I'm also looking forward to, now that we have LIGO online, there is a version of that that's going to go up into space that's called LISA. And that one is going to look at kind of longer wavelength gravitational waves. So it ought to get higher mass stuff. And yeah, so, and we have to get that, but like at a really low frequency, but maybe looking at the merging of supermassive black holes or intermediate mass black holes. And so we ought to be able to see things in very distant galaxies, and that is really exciting. That's many years off, but that definitely requires investments in new technologies. I mean, it's actually quite common when you propose new missions that you have to promise to develop the technology that you need to use. And that's part of how we kind of advance technology in astrophysics. And then I guess the last thing is more down to earth, the LSST survey, which is, it hasn't started yet, but it's going to be going on at the Vera Rubin Observatory in Chile. It's starting soon. We're not exactly sure when right now, but it's going to go for about 10 years, and it's going to basically get a movie of the changing sky, about a third of the sky, the southern hemisphere. And I'm really looking forward to that. There's going to be a lot of breakthroughs there. And one of the things I am most interested in is this kind of low-level flickering, because we're going to be able to look at a lot of galaxies for a long time at many different like band passes in the optical and near infrared. And so we're going to be able to look at like low-level variability and understand the kind of life cycle of these kind of like calm, even black holes that are lower luminosity. So I think combining those different things together is going to be really valuable, particularly.
And I think we also have a question from Eshwar about also future telescopes, maybe for Julie.
Yes, so he asks, are you excited for the launch of James Webb? And if you had a period in which to observe with it, what galaxy or region would you like to observe?
Yeah, that's a really, James Webb is going to change a lot of things. James Webb is going to open new windows on the universe that we wouldn't have been able to observe in that much detail before. So there's two aspects to it that are really new. One is the wavelength coverage, and the other is the sensitivity. So how faint things that we can observe. And so with James Webb, for these really, really active galaxies, we'll be able to observe the chemistry in them. And the chemistry not just in the currently star-forming regions, but perhaps in some of the older regions where there's existing stars. And using that, we'll be able to look at the gas and what the gas is doing in them, and perhaps the gas as it starts to create these stars rather than the gas that's already forming stars. And so that's going to be really exciting to be able to get such sensitivity and such resolution at those wavelengths.
And to get to know you a little bit better, and so people have an idea of different paths in astronomy, that's one of the things we do before ending. But maybe we could start with a question by Amaya, which is probably relevant to this section.
Yes, so Amaya asks, as lecturers at the university, you have quite a lot of contact with students and possibly also outreach events. Do you have any favorite experience that you had because of the outreach outside?
Brooke, it looks like you do have.
I mean, yes, I think I was just wondering which of us you wanted to start with that. I think as a lecturer, I would say best moment for me is when you see the aha moment with the student, when through whatever means you've helped them get to this point, they just get it. And then you know that they got it to the level that they're never going to forget it, right? Which is really amazing. And it's kind of it's like the holy grail. And it's really wonderful when it happens. I think in outreach and in public engagement and that kind of thing, there's a couple of examples. One of my favorite memories is from going to the Green Man Festival, and we had a stall there. That's a very like, I don't know, hippie granola, a lot of conservation, a lot of probably a lot of illegal substances happening there at the time, and people there are there to like listen to cool music and you know, have fun, but not necessarily to like do a science. And so it's really fun to have an interaction with somebody who didn't expect to, for example, be able to see a sunspot through a solar telescope. We had like people burst into tears because of that. You know, who knows if they were maybe on drugs or not. I'm not really sure about that one. But however, it was really cool. And then the other thing with that is you get like kids will come up to you, and sometimes kids, they just ask the question, they just get right to the heart of whatever it is that you kind of glossed over when you were explaining how cool black holes is. And they like ask you some question and you're like, I don't know. Nobody knows. I don't know. God, good question, 8-year-old, you know, and that's really, really fun because you get to then convey that the best part about science maybe is that we don't know a lot. So.
Julie, what about you?
Yeah, absolutely. I mean, I completely agree with Brooke. When you're teaching and you see someone just get it, and you can almost see the cogs turning and they click into place. And it's such a big deal when that happens, because once you get something at that level, you will be able to use it in the future. Whereas if you're memorizing parts of it, it's much harder to recall later. Whereas if you get it, then you're good. In terms of outreach and talking to people that aren't necessarily into science now or yet, I love showing them things that they never expected to see. So things like showing someone the craters on the moon through a telescope for the first time, or Saturn through a telescope, is something that, you know, we've got great pictures of these things. There's some excellent photographers and there's some excellent telescopes that show those things. But when someone sees that for the first time for themselves, you can see them light up and you can see them get really excited by it. And that's a really wonderful moment. And so that's really great to see. And then also showing people that science is accessible and it's not just for strange people, and that everyone has an option. And I find that particularly important because I didn't really understand when I was younger that you could do this sort of science as a career. I understood that you could go work in a lab doing R&D and developing things that had an immediate application. But I don't think I really understood that, no, you can spend your entire life researching things that there may be an application in the long run, or it may just be adding to the body of human knowledge, and that's still valuable. And so showing people that that's possible and that you can observe the sky, and most of the times when you do a new observation, yeah, you'll find a new galaxy. There's something there that no one else has ever seen before, and that they have that opportunity as well. It's really exciting.
And I guess with the equipment becoming cheaper and cheaper, I mean, even with the so-called, I guess, amateur astronomers are now discovering exosolar planets and competing with the professional ones, right? And then with platforms like Galaxy Zoo, you could just use your computer and you'll probably see something no one saw before. So that's really cool. So one thing that might be controversial for some astronomers, but do you have a favorite astronomer? It could be alive or historical, and for whatever reason. Julie.
Yeah, yeah, I do, absolutely. So my favorite astronomer is Jocelyn Bell Burnell, and she is absolutely awesome. So she is alive. She discovered a whole new category of sources in the universe when she was doing her PhD. She built an entire radio telescope, and her supervisor basically, you know, said to her, okay, go build this radio telescope and tell me what you find. And she found strange signals that she wasn't expecting to, and that he wasn't expecting to. And she figured them out, and they were pulsars. And her supervisor actually won the Nobel Prize for that discovery, and she didn't. But she's won awful lot of other prizes. And in fact, she's so humble that she says, you know, it was great not winning the Nobel Prize because I get to do all these other things instead. And one of the things that she's done recently that I think really just demonstrates her as a person is she won the Breakthrough Prize, which came with a big cash attachment. And she's converted that into a fund to help students who are from underrepresented groups to fund their PhDs. So she took her prize money and she's put it towards funding people that wouldn't otherwise be able to do science. And I just think that's amazing.
And yeah, I think this is the way to go. And Brooke, do you have a favorite astronomer? Is it also her?
Well, yeah, but she's like my tied for top, actually. But the other person is Vera Rubin, and Vera Rubin's amazing. She has passed away, and that was fairly recent. She also did not win the Nobel Prize for a Nobel Prize worthy discovery. That was that galaxies contain dark matter. That's a pretty big deal. And one of the things that, I mean, I got a chance to meet her when I was a PhD student, which was amazing. And she was just really supportive. Everyone always talked about her like she was just a great person and collaborator and very supportive. Jocelyn is as well, like just an incredibly supportive person, and especially of young scientists. And one of the things about Vera Rubin in particular is that, like, when she was deciding what she kind of like what her next project was going to be at, you know, a point in her early career, and she was looking around at some of the topics that were kind of the hot topics, and saw that a lot of them were like very competitive, and saw that she wasn't sure she liked the kind of science culture around some of it, and she was like, you know what, I just want to pursue this other weird question that I find kind of interesting, and I've got some data, and so let me go figure out what that's about. Even if I never get fame and glory for it, whatever, I just think it's really interesting and I genuinely want to know. And I think that that is a model for how to approach science. I think, you know, you have to take some level of like risk in terms of when you confront like the kind of pure ideal of science with the culture of doing science and making a career out of science, if that is your choice to do that. But she just went, I just want to do what's interesting to me, and we'll see what happens. And then she was like, why is this rotation curve flat? And everything went from there. And I really love that story. And I love that she was always really authentic about that, and was always just really generous, like with her time to speak to people, to mentor young scientists and so on.
And that is just really, really important, mentoring people. And I guess being role models, as you two are, I assume to many people already also watching us. So the other thing that's always curious to know is just how young people got like this thing to do astronomy. So I could start with Julie. You already mentioned that at least when you were very young, you didn't even know this was possible. I mean, to make a living out of it. But at some point, did you just knew that you wanted to be an astronomer, or that only came out very late?
I think I didn't know that I wanted to be an astronomer because I didn't know that I could. But I knew that I liked science, and I knew that I loved astronomy, and I thought stars were pretty and galaxies were awesome. And there were, you know, as I got into my late teens, there were these questions about whether the universe was flat or curved and going to expand forever or not, and that I found really interesting. And so I was interested in these things, but I didn't realize that you could have a career in these things. I'm not sure why I never made that connection, but I didn't. So science in general, I knew I wanted to be involved in, but I didn't know how. And I went to university doing physics and astronomy just because astronomy was great and I had to do physics to do that. And then I realized that, hey, you can do a PhD. So I thought I'd start doing that. And it was only kind of around about that point that I really kind of recognized that this was an option. But I don't think I ever internalized that I could do that. I recognized that people could do that, but not necessarily that I could do that. And it's credit to an awful lot of people throughout my career who have kind of pushed me and who have supported me and encouraged me to apply for different things and you know, given me those opportunities that I wouldn't necessarily have asked for myself.
And Brooke, was it similar for you as well? Or did you know from when you were super little, as some people apparently do, that they wanted to be an astronomer?
Yeah, I mean, I went through the phase for sure when I memorized the solar system, and, you know, I went through that phase, but then, you know, then I probably then was really into dinosaurs or something. I don't know. You know, as a kid, that was pretty normal, I guess. My parents both went to university, but they didn't like go on to do any grad school type work. And so I didn't, you know, I didn't have like a model for being an academic. I didn't have a model for like doing research. My parents both, you know, worked in a kind of, my dad worked in an office job and my mom was a flight attendant, and so worked with people a lot, but like it's a very different thing. But they both were like, you like science, huh? Cool. Let's see what we can do about that, you know? And so they were very supportive of me in that. I had an experience that it's weird. So I was like in 7th grade and we were doing something that was, for the first time, you could kind of call straight physics. I don't really remember what it was. Something to do with springs or something, I don't know. But I think it just didn't like go that well. I had never seen it before and I had like switched schools. And so everyone else had, and they were like, oh yeah, cool. They were like, no problem. And I was like, wait, what is this? I've never seen. And so I think I just decided like at that point, I guess physics isn't for me. Like, I guess this is too hard for me or something. I don't know, because everybody else gets it and I don't. So okay. But I like genetics and I like bio. So my whole school time, I thought I was going to be doing biochem or genetics or something. In fact, if I'd come up in the UK system, I would have changed too late to do physics and astro, because I didn't really do a lot of physics when I was in school. But when I was coming into my last year of school, I was an overachiever, so I had done all the like biology projects that I needed to do to like get into uni and whatever. And I was like, oh, let's do a different project for like a science fair project, which is a thing you do in the US. It's a very unique thing. And I had spoken to someone about doing something different, and she handed me a book on comets. And I read the book and I was like, that's cool. I wonder if, and I had this question about like, simulate, like if you could survive a small bit of organic material in like the core of a comet, if it entered the Earth's atmosphere, because at the time it was about whether comets brought water to the Earth in early days. And I was like, well, what if you could embed amino acids in there or something, right? And this is now a much more fully, I'm old, it was a long time ago. Anyway, so I basically took like a bunch, like a snowbally ice thing with some algae, and I bombed a hairdryer at it. And that was the closest I could get at the time. And then someone was like, maybe we should like try to put her together with someone who, but I had so much fun like doing this like janky experiment and like doing a question that was my idea. And I was just like, this is so cool. And then someone was like, why don't you take an astronomy course? And that was the big moment for me that I realized I could do this as a career. And so I entered university taking physics, not having really done it since 7th grade, but it all worked out.
Yeah, it did. So to finish, the final question. If you could time travel back and meet your younger self and you only had 30 seconds, what would you say to yourself? You only have 30 seconds.
Stop worrying about your grades and focus on learning the material and do what you want. Don't do what people expect of you because they expect it of you. Just do what you want. Trust your instincts, basically.
Yeah, I think it depends how far back we're going for me, but in short, it would be, you can do it, whatever it is. You know, those things do exist. There are opportunities, and you are just as able to do them as anyone else. So take those opportunities, apply for stuff, do whatever you want to do.
Sounds like a good way to finish. So I think we're running out of time. That's all we have time for today. Thank you so much, Brooke and Julie. Unfortunately, Joanne had a complication with his internet connection. This is all part of scientific experiment that this show is. So it's really brilliant to have you, and let's have a last round of applause. So thanks to everyone who watched, participated, and asked questions here on the chat. We will be back next week at 5:30 UK time with the amazing Rita Tujeru from St. Andrews and our very own Emma Dodd and David Orion from Lancaster University to talk about galaxy archaeology, galaxy mergers, globular clusters, and much more. So it's really going to be awesome. Until then, don't forget to subscribe right here and also watch other episodes on our YouTube channel. And you can also check out our entire program at xgal.uk. And if you speak Portuguese, you can also check out our episodes in Portuguese or watch them live Saturdays at 9 p.m. in Portugal and 5 p.m. in Brazil. Until then, remember to keep looking up, and I'll see you next time.
Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower. Welcome home, Columbia. Beautiful, beautiful.
You want us to take it up the hangar, Joe?
We're going to dust it off first.
3, 2, 1, 0, and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Roger roll, Atlantis.